Hello everyone, this is Sadat from Markenhive Game Studios. Today I will be showing you a modified version of the BRDF shader which I'm going to incorporate in my upcoming game project. As always, I will be linking to the source codes in the description below. First of all, let me apologize for the delay in uploading this video. I have become a bit busy with a new interesting project that I have taken up. I will be sharing details of that project once it comes along nicely. But for now, I might have a few delays in my video uploads, so I hope you'll bear with me on this. But I will try to maintain a weekly schedule. So let's look at what this shader can do. In order to show the shader, I have prepared a demo scene with some shader comparisons side by side, and I will show you why I needed to make this shader even though Godot ships with Burley shading. And the first monkey that you can see is colored using the default shader. I've kept a little global illumination in the scene to soften the shadows and make the models look nicer. As you can see, tweaking the parameters in the spatial shader yields nice results, but it does not allow me to get the right amount of gloss to my model. So to cover the issue, I tried the Blin Fong shading. It yields a very nice plastic look, but that is about it. Nothing else changes. Now the next shader that I created was the Oren Nair shader. It's a good tweak for plasticity and roughness, but no metallic sheen. I also didn't like the fact that the light abruptly cuts off in the edge, so I decided to look into Disney's BRDF shader, since it allows me to pretty much tweak every aspect of the material. However, the full implementation is a bit costly, so I decided to isolate the most contributing factors and implement those only. Now, before I get into the code, let me show you some examples. Here, the first thing that you're seeing is a gold. Well, it's a gold monkey. It's a metallic effect that I've given using the BRDF shader. The immediate next one is a blue plastic monkey. This is also using the exact same shader. I just changed the parameters, and as you can see, the material looks very different. Now for the third one, if you look at the third one, you'd see that it resembles skin. That is because of the subsurface scattering that I've included in this shader. However, for this particular monkey, I'm using a double pass rendering. So I'm actually using two different material nodes of the same shader to create this really nice skin texture. And this last one that you see is it's a sort of a radiance material. It is not a physically based material, but you can create effects using this shader as well. So moving on, let me get to the code. Before I get to the code, let me shift to Visual Studio. So now that we're in Visual Studio, let's get started with the code. So the first function that we will be looking at is the light function, where I define the constant value of pi first. Then I convert the color space of the albedo color and the light color into this interesting little color scheme that I found in the BRDF paper, which is the Montulin. It returns the color values raised to the power of 2.2. So for every single color component, which is the red, green, and blue, I raise it up to 2.2. This makes the colors look a lot more vibrant and the fall off looks so much nicer. So I decided to stick to it. There has not been a lot of details on how this works, so I really don't know a lot of details on the Montulin function. Next up, the luminosity of the albedo is being calculated based on 0.3 contribution from the red color, 0.6 contribution from the green color, and the 0.1 contribution from the blue color. The logic behind it is that green usually seems brighter, significantly brighter than red or blue, and the researchers at Disney found out a really nice approximation of calculating the luminosity of a color based on this. So anyways, after that I calculate all my half vector n.l, n.l, n.v, n.h, n.l.h. These are all dot products that I'll be needing in the next functions. Then I calculate the Fresnel values for this. Now the Fresnel function that I'm using for this shader here is a much more simplified approximation of actual Fresnel. This is not based on physically accurate Fresnel, but rather a very nice looking approximation, which basically is a clamped 1 minus L dot H clamped to 0 and 1 raised to the power of 5, which is a lot simpler than the previous function I was using. Now once I have the Fresnel, this is where I've done something a bit differently. What I've done is, instead of taking the range of 0 to 1 for n dot L, I've decided to keep using the entire range of all the dot values. So normally a dot value ranges from +1 to -1. So I've shifted the entire range within the range of 0 and 1 instead of cutting it off at 0. Now for me, I like this because it creates a much more smoother transition between the light and the shadowed areas, but you could choose to use the standard mechanism. So this is where I've done things a bit differently. So this is where the diffuse light is being calculated. The first thing I'm doing is I'm filling the entire thing up with a basic Lambertian diffuse, which is Phong diffuse, where I use the value of pi, a smooth step between 0 and 1 based on n dot L, and then I create the diffuse component, which is light color times the albedo color divided by pi times theta, and I return this component. Now afterwards, this is where I mix between surface scattering and subsurface scattering. Now diffused light is light that we see from the diffused scattering of light from rough surfaces. So there are two kinds of diffusion that happens in materials. One is surface diffusion, the other is subsurface diffusion. And if you're having a lot more subsurface diffusion, you'll have a lot less surface diffusion. That is how I am making this work. It is an approximation. This is not physically accurate, but it gives a nice result. So anyways, to calculate the surface diffusion, I just need the L dot H, the Fresnel of n dot L, and the Fresnel of n dot V. What I'm doing here is I'm taking the absolute value of the Fresnels. I'm finding out the adjacent, the Fresnel at the 90-degree adjacency to light, and I'm giving it to the intensity value of approximately 1.5, and then I'm mixing it based on the n dot L Fresnel and the n dot V Fresnel. Right? A very similar process is being carried out for the subsurface diffuse, where I use the L dot H and the Fresnel of n dot L, n dot V, and the n dot L and the n dot V. Now, both of these functions are taken as it is from the BRDF paper, and this works pretty nicely. Going to a detail of the entire mathematical functionality of this is beyond the scope of this tutorial. I might start a new set of tutorials on the mathematical side of all these algorithms and the basis of the mathematics, but that's something for a later date when I have a bit more time on my hand. Alright, so this is where the adjacency is being calculated. As the previous one, you calculate the adjacent Fresnel here again, but this time you use the roughness value as well. And then this is where the subsurface diffusion is being carried out. Just like before, it's a mix of the adjacent Fresnel between the n dot L and the n dot V, and then there's a little intensity adjustment based on 1.25 times the subsurface diffusion times 1 by n dot L plus n dot V minus 0.5, and adjust the whole thing by by 0.5. So the next thing that I calculate here is the metallic contribution to the color. So the metallic contribution to the color, it goes a bit like this. The more metallic the color is, the less diffuse light it will give off, because ideally the perfect metal does not have any diffusion in the surface, which means any light that has been refracted into the surface is going to be absorbed, and only the directly reflected light, which is the specular light, will be given off. So the more metallic the material becomes, the less diffuse light it will emit. Hence the 1 minus metallic parameter. So up to this, the diffuse component has been calculated. Next up is the specular component of the light. Here it's a mix of the sheen and a Lambertian specular. No, based on the n dot h. Okay, so let's just calculate the Lambertian specular first. It's the same specular function for a Blindfong shader, which is power of n dot h times 256, and it's a max of specularity and 0.001. And theta is again smooth step of n dot l between 0 and 1. Now, this is where I've done a little interesting thing. I've actually applied a metallic multiplier to it, so that when the light, so basically the way that the metallic component of specularity is being calculated in BRDF is through anisotropic GGX. I've decided to cut down on those calculations and just simply approximate this part. So the more metallic the material is, the more intense the specular lighting will become. And I will be taking the maximum value between the specular tint and the metallic property for the specular color property. So this is the slight change that I've done in the specular side. And as for the Burley sheen, this is also the exact sheen that you see in the standard BRDF implementation. However, I've done a little adjustment to it, which is I've multiplied the return value by 2 times, and I've added subsurface as an additional property to the Fresnel value. Now this allows me to extend the sheen further based on subsurface scattering, which basically emulates the light diffusion within the material. So just by doing this, I can cut off quite a lot of the anisotropic GGX functions and have a pretty similar looking effect. And again, the diffused light is being mixed based on the n dot h, which is the half vector, which is basically the dot product of the normal and the half vector. Finally, I divide the diffused light by pi and multiply it by attenuation, and that's it. That is my simplified base BRDF shader. I hope you like this tutorial. In the future, I plan on making a tutorial which covers the entire BRDF shader in detail. And if you like this, please feel free to click like and subscribe, and I'll see you on the next tutorial. Have a good day.